That's such a good service.
Okay, so class ends and I wait for you to leave and then I stand here and I'm a week early for class.
Still,
Not a week early, 2 days early.
you were totally no.
Yeah, I was close.
No reason.
Yeah, no, not for no reason, because you were missing seats. I wasn't even close.
This is nice. This is now.
Okay, then better.
Oh, I see.
I want your seat. I have this seat, it's so much better.
So let's say the seat is better.
Someone be wrong.
Yeah, the seat is better. Why'd you say this?
I'm dating. I felt. No, thanks. I can't remember that. Next one.
So tomorrow you're really gonna be at home. So I don't know. It is quite. What if that wasn't at my seal?
And that would be your own bullseye.
No, this for you, you're the one who looked. Yes, yes.
Because you wouldn't be in your bag right. We just have to carry it out right for that. Yeah.
That's what you're. Made me anxious.
Yeah, and we're talking about like there's no reason there are we could talk about the also wider than the last year. Bring that up. There's oh boy.
There you
Oh
go.
boy.
This is the best water bottle I've ever had. It's so easy to.
Boy.
Just wash it.
Yeah, plastic will eventually fail. Unfortunately.
I'm getting ratio. But metal has a metallic taste.
Not
always.
I cannot taste mine, so it's okay. All right. Oh, right. Gotta go. I cannot do it today. Dang it. Okay.
What were the last ones?
Like I'm blasphemizing. It's black and white to get another easy power. You done this?
Is my name?
Yeah, there's nothing.
Now you just said that for no apparent reason.
No, I ain't.
No, I know.
But I would just say, like,
Because I did.
All right, it is noon time, so we're gonna get started here. So first thing first, we do have a homework assignment due on Wednesday, not today, Wednesday. I took a quick look, not a whole lot of people have started with the homework. So, which is okay with me. I mean, it's not a really difficult homework assignment. But I would suggest, at least, clicking it open because you don't have to submit until the last moment. So you can basically have it open, look at all the questions, spend as much time as you want to ponder, to think, to review the material until you feel 100% sure about your answers. But I would start early. So that's a suggestion. That's a dad thing for me to do. So you can totally ignore. So that's up to you. All right. So I do want to bring up some stuff that I did not mention before. Okay, this is the MBTI, Myers-Briggs Type Indicator personality stuff. I don't even remember what I typed in this one. But if you have not done a personality test, this is interesting. Okay, they're not 100% accurate. Some people completely disagree with the outcome of the assessment, and some people say that's exactly me, except I could not put it that way. I could not actually tell other people that much about myself, but the test result, actually reflects me. So it's interesting. It's interesting from the perspective of you might change the way you study, okay, depending on your personality type. Okay, so the strategy that or the most effective strategy that you can use may depend on your personality type. Is that okay so far? All right. All I can say is, when I find out that most people are not like me, I go like, oh, so my assumptions have been wrong for the past like 4 decades, 5 decades. It was profound. And also, for certain types of people, you tend to study alone because you don't want other people to interfere, to disturb you, to interrupt you when you're actually studying. For some other people, it might actually be necessary to study with somebody else. So I think this can be helpful. Okay, that's all I'm saying. It can be helpful. All right, so moving on. I was just talking to Damon. Some of you might have taken his classes about intrinsic drive when people take classes. In other words, what is your motivation to take classes and to be in a class, and what does it take to motivate you to study, to review the material, to do the homework? So that's a question that I cannot answer for you because I think it's very, very individual. I can only tell you about myself. Yes, I do talk about myself a lot, but I can tell you I can give you one sample point. When I was in college, which was a long time ago, okay, I went to all my classes with enthusiasm. Every time I walk into a classroom, when the class is ready to start, my thinking was, okay, teacher, teach me something new today. So it was exciting every single day. And it was fun. When homework assignments were due in 2 weeks, I would have done those in 2 days. Not because, I want to show other people that I have done it in 2 days, because I never tell anyone in my class that I got the homework done already. Well, not for the reasons that you think. Okay, because my English was really poor at the time. I could read, I could listen, I could write, but I could not speak. Okay, so, or at least I did not feel comfortable talking. So I had no friends, I did not know anyone in my class. I just sat, at the front of the entire classroom and just write notes. And when the teacher makes a very obvious mistake in class, I would just go like, think the teacher is wrong. Check on this later. Instead of raising my hand and go like, I think you're wrong about that one. So in that way, I might have sabotaged my entire class on a few occasions. So anyway, it's a different mentality. So I'm not sure what is motivating you to come to class. what's motivating you to take classes or to pursue computer science, I can only tell you about myself. So something for you to think about. All right, so we are still on quantifiers. So we'll go ahead and continue with quantifiers. And if you guys have any questions over the weekend, if you want me to go over something again, that's not a problem. Especially if you ask specific questions like, I'm not sure about this thing here. One person asked me about, a question of whether equivalency or if and only if is commutative. And the answer is yes, it is commutative. Okay, so before I go any further, does everybody understand what I mean about what I just said? The operator of if and only if is commutative. So what does it mean? Okay, so I want someone other than myself to explain what that sentence or what that statement was actually saying.
And it goes both directions.
It goes in both directions. Very good. So that means if okay, let me put it back. X if and only if y is the same thing as y if and only if x. Okay, that's commutative. So the question is, I answered yes, it is commutative. But how do we know that? How can we know that if and only if as an operator, the double-sided arrow thing is commutative? And of course, some people may say, but professor, you're supposed to know that and you're supposed to teach me, but I'm going to tell you one thing. You should know that too, because I have shown you one tool that is super useful and it can be used to prove that if and only if is commutative. So what tool do you think it is? It's the truth table. Very good. And if that is the truth table, how do we use the truth table to show that x if and only if y is really the same thing as y if and only if x?
The truth table for those cases.
Well, the truth table tells you all four possible cases, right? The value of x and the value of y, right? So what you need to know is what if x and y are different? Because when they are the same, it doesn't matter. When they are different, then you have to ask if true is on this side and false is on this side, what result do I get? When false is on this side and true is on this side, what do I get? If those two rows are exactly the same, then the operator is commutative. Does that make sense to you? In fact, all of the operators with one single exception are commutative. Conjunction is commutative. X and y, y then x, they mean exactly the same thing. Or disjunction is commutative. X or y versus y or x is it's exactly the same thing. And it shows in the truth table. If and only if, once again, is commutative. Exclusive or is commutative. The one that is not commutative is
Difference.
difference is not, but it's not a Boolean operator. Then is commutative. Implication is the only one that is not commutative. So, so one thing you might want to do is to kind of go back to the truth table and prove to yourself, okay, why implication is the only one that is not commutative. Yes.
So you're saying that you swap x and y on the truth table, and
Not so much swapping in the truth table. Let me see if I can show you here. Because I cannot get set up my split screen as usual. So I'm using only one screen, which means when I'm recording this, it's only recording one particular window. So everything I do, they have to be in this window. But that's okay, I can get around that limitation by using Google Doc instead of Joplin. Google Doc is okay. I mean, it can get a lot of things done. It's just not as good as Joplin because I'm much more used to Joplin. So I'm going to insert a table. And I think there's a little tool somewhere to insert a table. I have to find it. Tools, no. Format, no. Insert has to be somewhere here. I think it's insert table of contents. Where's the table thing?
He was at the top when you hit insert.
Okay. Insert.
Gotta scroll up.
Hmm?
You scroll up and you'll see table.
Oh, okay, so already scroll down. Thank you. There we go. So we need X, Y, so two columns just for that, one column for the result of the operator, which in this case is if and only if. And then we need 5 rows altogether. One is the header, and then the other 4 correspond to the actual true false values. So there we go. Okay, excellent. So we got X, Y, and then we have X if and only if Y. If I want to be fancy, it does take up a little bit of time. I can go to insert equation. And I think this one does recognize LaTeX format. So I can use left, right arrow, Y. Yep, it does. Nice. And then we have false, false, true, true. And then we have, oops, false, true, false, true. All right, so when the two values are the same and the same row, we don't have to worry about those, okay? Because X and Y are the same, so there's no switching the order between those two, it doesn't matter for these rows. So in this case, if and only if this is actually true, this is also true. These are the only ones that are false, right? So these are false, this is false. The truth table itself is not new. Okay, so there's really no need to copy this down. But what you might want to take note of is, why do we know from this truth table that if it's X, if and only if Y is commutative? It's not about X, Y. It's not about X is on the left, Y is on the right. It is about which side has a 1 and which side has a 0. Now, this is easy because in Boolean operator, each side can only be a 0 or 1. So if you look at the middle 2 rows here, 0, 1 being XY, and then 1, 0 being XY, those are the only 2 rows, okay, that can determine whether an operator is commutative or not. If these 2 rows end up with exactly the same value, then the operator is commutative. Because if you exchange the order, which side has the 0 and which side has the 1, it doesn't change the outcome. And that is the definition of how an operator is commutative. Are we good so far? Yes? Okay. So if you're looking at this and go like, yep, I'm getting this, because of algebra, because the concept of commutative is from algebra, then it's good. Okay, you're connecting what you're learning today with something that you have already learned, and that's good. If you're thinking, I'm not really quite sure what commutative means, then you might want to look it up, because algebra is really important. I can almost say for sure that calculus is not very useful in computer science for the most part. Okay, but algebra is. Yes, go ahead.
Just wondering why having X and Y.
Why X and Y are 0, right? It is not false. Because, okay, well, that's an interesting question too. So in order to answer that question, let me answer this. I'll ask you another question, because that's my tendency, is to answer a question with more questions. So what is the definition of if and only if? If I don't give you the truth table, if I don't tell you that, oh, just take this table for granted, this is how if and only if is defined, how do you define if and only if? That becomes the next question. Oops, inserting the equation at the wrong spot. So how do we answer that particular question? We actually talked about it. In the module, it has already defined if and only if using operators that we already know. So which one is it? Yes.
X implies Y and Y implies X.
Yes. So my recommendation is to utilize this X definition. So in other words, let me say that here, X left, right arrow, Y. is really defined exactly the same way as X implies Y and Y implies X. So use this definition, make your own truth table, which means you have to know what is the truth table of implication to begin with, but that is also given to you. Implication itself can also be defined in something else, right? Okay, I hope you guys are remembering this because I'm just checking whether you have been reviewing the material, whether you have, you know at least where to find the definitions and so on and so forth. So X implies Y is exactly the same thing as the negation of X or Y. So negation, the truth table of negation is super easy because not true is false, not false is true. Disjunction, which is what this symbol is representing, should be also pretty easy because you have been using the disjunction operator in C++ programming for a while. So are we doing okay so far? So this is not new material, but I think it's a good assessment of how much you understand the current material and how you can relate this stuff to the more elemental forms of the operators. So this is a pretty good checkup, I would say. It's a good checkup for everybody. If you're looking at this and go like, yeah, I got all this, great. If not, well, maybe a little bit more time to review the content. It would be helpful. So we okay so far? Is the font size okay especially for people in the back? Yes, okay, because I can potentially make it a little bit bigger. Like I still got space on the screen. All right, so if this is all good, then we can continue on with the current material, which is basic quantifiers. And last time I was using some code to specify, the quantifier and filtering. Okay, filtering was what we talked about last time. So the notation that I was using here is this. Okay, this was the last topic that we talked about in class last Wednesday. And the way I can remember what I talked about last time is I just watched my own video. Okay, just slide all the way to the end, maybe the last 10 or 5 minutes. That reminds me, oh, okay, so we are there. This is where we're going to pick up today. So I would highly recommend that you guys do the same. You don't have to rewatch the entire 80 minutes. That's a killer. Okay, but if you just kind of go back to the last 10 minutes or so, or you can play really fast, just kind of skip every 10 seconds or so, that will still give you a kind of a quick reminder of where we left off last time, and it can be helpful. All right, so this is just a notation thing. If I, this is how I express, this is only important, okay? The negation of P of E, which is just an example, it's only important if E is, an element of X. For all the other stuff in the entire universe that is not a part of X, I don't care, okay? And this is how we can express it, but this is really kind of cumbersome. This is how I would normally do it in class, which is to use the element of X and move it outside of the parentheses that specifies exactly what condition are we really interested in for things that are in the set X. Is that okay? So it really is just a notation. It's a shorthand. How much are we saving? We are saving an extra E because E only appears once here, and also the implication operator, which is entirely missing here. That's all we're saving. Is that okay? This is a filtering mechanism, which basically means for anything other than things that are in the set X, we don't really care. Do not let them change the true or false of the entire quantified expression. Is that okay? And by the way, what is the default value of the universal quantifier? I gave you C code, pseudo C code last time that basically outlines, how for all works. So what is the default value? What is the variable result initialized to? What is the initialized value of result, which is a local variable of the code that I gave you for all? It's true, very good. So that means, as long as, things that are not in the set of X is not changing the result to false, this is going to work. And implication works just like that, because implication, which we also explored a little bit earlier here, because implication can also be defined as not the left-hand side or the right-hand side. So if I go back to what we are dealing with here, so that means if something is not an element of X, the implication automatically gives you a value of true. And inside the loop, how do we combine the new value of P of X with the current value of result in the code that I gave you that specifies the logic of for all? Do you guys remember which operator were we using? It can be and or. Okay, so you have a 50% chance of guessing the right one. Is and. It doesn't make sense to use or, because if result is initialized to true already, and you're saying result or something, there's no way result can become false. So if a subroutine is returning true all the time, why bother to write the subroutine, right? So there are many indicators, even if you do not remember whatsoever, okay, what operator we were using, the fact the result was initialized to true is already giving you a pretty good hint that out of and or, that operator to combine the existing value of result with the new value, which is P of the element, has to be an and. Is that okay? All right. So we are moving on to there exist. So this is the existential operator. So without this part here, which is E is in X and blah, 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 then we are basically asking, out of the entire universe, can we find at least one thing that makes P of X, P of E true? Okay, but most of the time, we don't really care about everything in the entire universe. For instance, I may only be interested in prime numbers, even numbers, certain range of the integer and so on and so forth. So how do I narrow that focus and go like, I don't care about the rest of the entire universe. I only care about these things. Okay, so how do we do that? How do we do that? So the mechanism to do that is to use a conjunction in this case. In other words, this is basically saying if for anything that is in the universe, but it is not an element of X, this is going to be false. The left-hand side of the conjunction is going to be false, which means the conjunction is going to be false. And as a result, it is not changing the default value of there exist. That's because in there exist, okay, the local variable result is initialized to false. Are we good so far? All right. So I do have to say this. I know, my dad instinct is kicking in again. This is one of those things. This is why being a parent is called a life-changing experience, because once you're a dad, you treat everybody else like a kid. I will try my best to refrain from doing that, but unfortunately, sometimes it just seeps through. Okay, all of you have dads, and you can probably tell that your dad would do the same thing to other people about your age. Is that true or not? Or am I the only person who's doing it? Okay, all right. Because my own son, often tells me, Dad, not everybody is like you. And not in a complimentary way. Yeah. All right, so getting back to this. So if you are looking at this and looking and interpreting what I just said, okay, the subroutine that represents the logic of there exist, okay, and the default value or the initialized value of result is false, and you're coming up empty completely, that is a good indicator that you need to review and reread the notes in class. Now, if you did not take any notes, which I have noticed, okay, some people are not been taking notes at all. That's okay, because I got it recorded. So you can rewatch the video. If you do not have your own notes to go over, I would suggest you watching the video again. All right, yes.
So you can kind of think of like, I just want to like put there exists in all in like English. You can kind of think of like there exists as like we need only one hit out of like an
Yes.
array.
Mhm.
And for all, we need every element in the array to be
Right.
Like for example, like there exists and we have E is an element of X and the predicate.
Mhm.
Only one of the elements in the array actually needs to like. Okay.
Exactly. But the filtering mechanism is still useful. Okay. So let's pick up that example that we used before. And this time, P of E is basically returning true if and only if E is a good professor. Okay. So let me say that one more time. P of E is true if and only if E is a quote unquote good professor. I don't really care how you qualify whether a professor is good or not, but we'll just say that is how we qualify so that P of E returns true. Is that okay? So without the filtering mechanism, it is asking, is there anything in the entire universe such that that thing is a good professor? You go like, yeah, I know quite a few professors at CRC who are really good professors. But the question that I really want you to answer is, are there any good professors at ARC? Because that's where I work, right? So the filtering mechanism basically needs to do one thing. If that person or if that thing is not a professor at ARC, it should give you false. Because I only care. The question is, out of all the professors at ARC, is there at least one who's good? Is that okay? So that means the set X in this case would be the set of all ARC professors. And as a result, if E is not an element of X, for instance, we're looking at Sunny Huang from CRC, well, the default answer to this entire question is false because the element of part is false, and because there's a conjunction here, when the left-hand side of the conjunction is false, the entire conjunction is false. So that is not going to impact the answer of whether there is at least one good professor at ARC. Does that make sense? All right. But the filtering mechanism is different. When we have for all, the filtering mechanism is an implication because we want a default value to be true. Okay, for anything other than elements in X, we want the answer to be true. But in the case of there exist, we want the default answer to be false. So for anything other than elements of X, we want the answer to be false. So the shorthand once again is this, which is there exists E in X such that P of E. So I'm saving myself a little bit of typing, which with the parentheses here, one extra E, and also the conjunction symbol. Not a whole lot, but I think in terms of the context, it does make it easier to read. So are we good so far in terms of the filtering mechanism and the shorthand of how we specify how we want to filter the existential, which is the E thing, and the universal quantifier, which is the for all, which is the A that is inverted. We good so far? Are there any questions? There are no questions. All right. So if there are no questions, then we're going to go back to our main module here. This is the Canvas module. And we're going to go all the way down to set theory using quantifiers. So we are basically revisiting all the operators. And we just want to answer the question of, now that we have quantifiers, can we make a better use or can we define those operators in a different way? So the first one is equality. And we are given two items, X and Y. How do we know they are the same? First of all, if one is a set and the other one is not, then x equals y is going to be false to begin with. So this is pretty easy to define, but it's not really, okay, I want to relate this to programming, not just mathematics. So in terms of programming, we are basically just saying if the types do not match, then it automatically returns a value of 0. That is not always the case when you're programming. In other words, you can have one thing on one side that has one type, and you can have another thing on the other side that has a different type, and the equality would still work. Because in many programming languages, type coercion, which means the tool itself is looking at the two sides and go like, can I kind of make one look like the other one? It can work, which can also cause a lot of problems. Scripting languages, particularly like JavaScript, is the worst offender of this type of programming mistake. Because when you use equal, equal, I mean, you guys all know equal, equal, which is you're just checking for the values being the same in C++. In JavaScript, if one is a string and the other one is a numerical value, it would actually go like, can I look at the string as a numerical value? And then tell you whether they are the same if I were to look at the string as a numerical value, which is not cool, okay, in some cases. It's great in some cases, not so great in some other cases. So in those programming languages like JavaScript, there's another operator, which is a triple equal. Equal, equal, equal. So in a triple equal, if the types do not match, it will automatically give you an answer of false. It is only when the types match and the value also match that it will be a true value. So once again, not exactly a CISP440 topic, but since we're talking about types on the two sides of checking whether things are the same, well, might as well talk about that a little bit. All right, so moving on. So given that x and y are not sets, then the normal comparison applies. So you compare integers, you compare real numbers, okay? So however you want to compare the elements is the way you do it. Now, if x and y are the same, then we can say the following. X and y are the same if and only if everything that is in x it is also in y, and everything that is in y, it is also in x. Now, if I miss one of these two, okay, look at this conjunction here. If one side is missing, it doesn't work anymore. It doesn't work as what I intended, because in that case, one set can be larger. In other words, we have a proper subset of another one. It will still be considering those two to be the same. So that's why it is important to have this conjunction here to basically say that everything in x is also in y, and everything in y is also in x. Is that okay? All right. So a more concise statement is to move the if and only if, use if and only if, so that this time it says, for everything in the entire universe, okay, so this time there's no pre-filtering, but the expression inside, is changed. If E is in X, if and only if E is in Y. In other words, if E is not in X, it better not be in Y. Is that okay? All right. So intuitively, are we seeing this is really saying the same thing as what we said before I introduced quantifiers. Okay, all right. So set description is kind of the same thing. This is a shorthand. Oops. Let me scroll down here. So this is a shorthand. Okay, if I need to describe the membership of a set, this is one way to do it. E is a set such that every element X in E has to meet the requirement of making P of X true. So that is the same thing as saying for everything under the sun, well, I shouldn't say under the sun, but everything in the entire universe, if something is in E, then if an only, okay, something is in E, if and only if P of X is true. So this notation here is the same as this notation here. But this time I'm using a for all quantifier as opposed to before, there was no universal quantifier. Because without the universal quantifier, then the question is, okay, hold on a second here. is the implied quantifier existential, which means if I can find one thing of the, if I can find one thing in the set to make the P of X true, that means, the entire set, is, meets that requirement, or what? So this time it is very explicit. It's using a universal quantifier. Is that okay? Any questions? No questions? All right. So moving on to the empty set. Empty set is interesting because if S is an empty set, then we can also say this. The negation applies to the entire expression here. So this is basically saying it is not the case that there exists something in the entire universe, so that something is an element of S. It's a very roundabout way of saying this set has nothing. Okay, but it does illustrate the use of the existential quantifier. But this expression, okay, let me copy this expression because I can also show you how it is equivalent to something else. Okay, so it is always good to kind of look at, I wonder if there's a different way to express exactly the same thing. So that's what we're looking at here. Let me also insert, okay, I can magnify a little bit because I think it might be a little bit small for people in the back. So let me magnify a little bit. Insert equation. I wish there's a hotkey to do this, because I do this a lot. And now we can paste that thing in. And it doesn't seem to like that when it's pasted. That is interesting. Okay, what if I get out of here? Huh, it does not like it when I paste the whole thing in. All right. So I probably have to do it by hand. All right, it is not the case that there exists X such that P of X is true. That's basically what we had before. So it just doesn't like, the whole thing pasted in because I think it's trying to process as I type. So the logic doesn't work when the whole thing is pasted. So this is saying exactly the same thing as it is not the case. And then inside, oh, I take it back. Okay, take it back. We use a for all on the outside. So it is the same thing as saying for all X in the entire universe. And it is not the case that P of X, oh, I need space here, P of X is true. So in our case, P of X is to say X is an element of, what did I use? S here. And in this case, well, I mean, it's the same thing, except we just replace P of X with X is an element of S. All right, so does that make sense to you? Okay, if I say it is not the case that I can find something and that such that something is in S, is that really saying the same thing as everything in the entire universe? For everything that is in the entire universe, it is not the case that X is in S. They should say exactly the same thing, just said in a slightly different way. Does that make sense? So here's my question to you, okay? In a colloquial way, when you talk to your friends in a very non-formal way, when you want to say not every, okay, do you intend to say it does not, I cannot find any blah, 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 as opposed to everything such that it is not the case? Which one do you prefer? Now, this is a question for you to kind of think about when you talk to some other people. Are we okay so far with these concepts? Okay. So up to this point, I really have no idea why discrete math has a number of 440. Why is it considered a difficult class? Because most of the things I have talked about, you intuitively use those in normal daily conversation. Okay, every time you say every, okay, you're using the universal quantifier. Every time you say some, you're using the existential quantifier. And or not, goes without saying, okay? Implication is every time you say if. That's implication. Now, if and only if is a little bit awkward. Most people do not use it when they are supposed to use it. Because if and only if is actually what people meant when sometimes they only say if. All right, so the difficult part up to this point of this class are the symbols, okay? Look at all those mumbo jumbo. I have no idea what they mean, but that means you just have to get familiarized with the symbols, which does not happen naturally unless you put time into it. It's just like how you learn every language. Mathematics is a language, just like C++ is a language. All right, are we okay so far? Question?
Why exactly is CISP 370 co-reference?
370?
Yes.
CISP 370 is Visual Basic.
See it?
430? 430 is data structure.
Yeah.
And the question is, why is it related to this class? How does it relate to this class? Why is it a co-requisite? All right, so when we get into the later concepts, we'll be talking about proof by induction and recursive definitions and stuff like that. And 430 is one class that guarantees to talk about recursion. 360 may talk about recursion. The way that I taught CISP 300, I talk about recursion. I also talk about recursion in CISP 310, but that's just me. But no one can teach 430 without using recursion. So that's kind of why it is a co-requisite. All right. So getting back to more notations. So we are looking at this module here. All right, intersection and union. Well, I'm using the membership thing again. So for everything in the entire universe, X is a member of X union intersecting with B, if and only if the same X is in A and it is also in B. It's really saying the same thing as last time, except this time we put this universal quantifier on the outside. The rest is pretty much the same thing. Is that okay? Question? Oh, okay. And then union is kind of the opposite. You can kind of see the similarity here. Intersection and conjunction, they have a certain resemblance, like the open end is down, and then union and or, they both have the open end pointing up, because those are related concepts. One applies to set, the other one applies to logic. All right, Cartesian product. So with Cartesian product, it is basically, I'm using the filtering mechanism. So if we want to know what is A Cartesian product with B, then we say for every X in A and for every Y in B, XY is in AB, and for every XY in A Cartesian product with B, X is in A and Y is in B. It is important to have both parts, because if you only have one part of the conjunction, then you can end up with a, okay, let's think about this, okay? Let's just say that with this conjunction here, we only have the left-hand side. What is the implication of that? The implication of that, okay, let's just say this part does not exist, okay? Does everybody understand what I'm talking about? So we'll pretend the right-hand side does not exist. So if the right-hand side does not exist, the Cartesian product can potentially have additional things, and it will still make this expression true. Because if this thing here, let's not call this the Cartesian product of A and B, we'll call this AXB, okay? So AXB can contain additional elements, and this whole thing will still be true. But that's not how I want Cartesian product to be defined. So I need the other one too, which is basically saying, if I take anything, any two tuple out of the Cartesian product between A and B, I'd better find the first one in A and the second one in B. So this way, it cannot be bigger, cannot contain additional elements. So the left-hand side, make sure the Cartesian product contain any, it makes sure it has everything that we need. And then the second one, make sure that we don't have anything extra in the Cartesian product. And both of them are required to precisely define what is the Cartesian product. Are we okay so far? Yes.
How do we read the left side?
Huh?
How do we read the left side?
How do we read it? How do we read it? For every element x in A and for every element y in B, x, y in a two tuple has to be in the Cartesian product of x and y. But I mean, that's how I would read it. And for a lot of this stuff here, it's important to kind of be able to look at this without having me to read it out in English, because that's the whole idea is we don't want to use natural language. So we want to be able to map it directly from the symbol to the meaning of the expression without having to go through the natural language part. I mean, that's, I know initially it is a little difficult, but eventually we want to do that. I can give you an analogy. How many of you still use flowcharts when you're writing code in 430 or 400 or 401? Okay. But flowcharts get really complicated and difficult to maintain for those classes, right? So, okay, let me change the question. Do you need a flowchart to remind you what a while loop does? The answer is no. Okay, you see a while loop, you automatically associate, oh, here's the condition, this is the body. We come in, checking the condition first. If it is true, we perform one iteration of the loop. Then we go back and then we check the condition again. You don't have to spell it out anymore, right? You intuitively, you look at the structure of the syntax and you know what it's supposed to do. So that's what I want you guys to be able to do in this class, is to look at the expressions and be able to translate that directly in your mind to what it means without going through the natural language part. Because natural language is not precise. All right. So it does take time. Okay, it takes a lot of exercise to do that. And then we have a subset. A is a subset of B if and only if every element in A is also found in B. Okay. A is a proper subset of B if and only if A is a subset of B and there exists at least one thing in B and that thing is not in A. So I find the universal and substantial quantifier to really help to clarify the concepts. All right. So I'm just going to pause here to see if there are any questions. So up to this point, okay, all we are doing up to this point is to build up the vocabulary that we need in order to express something else. And that something else is also really just the vocabulary that we need to express something that is meaningful and actually useful in computer science. How many people get this feeling at this point of this class within this context and go like, I really don't see myself using any one of these operators in programming? I'll be the first one to raise my hand, okay? From that perspective, it's like, how does this have anything to do with programming? Well, in that case, have you looked up algorithms? Okay, and some, and I mean, complicated, complex algorithms, such as Dijkstra's algorithm, the A-star algorithm, that we will actually talk about in this class. Those algorithms actually make use of the set notation. It does not use arrays, but it uses the set notation to see if something is in a collection or not. Now, how do you maintain that collection? You can use the template class in C++. Sure, that's one way to do it. You can use the built-in class set in JavaScript. If you're programming in JavaScript, sure, fine. If you're dealing with a very small range of integers, you can even use the bitmap approach. It doesn't matter, but it's the concept that is important, that we need the concept of a set in order to implement those algorithms. All right. So I'm just going to leave this one on just in case there are questions later on, and then we'll move on to the next topic. So we are moving on to something that's actually useful. So we are going to look at functions. So you can see that, the way I talk about, I go through these links here is sequential. So that means, if you say, I got a bunch of time on my hand, I got nothing else to do, you can read ahead of the class. And all you have to do is to follow the order, and go like, what is the next link? What is the next link? What is the next link? And that way you can actually read way ahead of the class, which is great, okay, if you can do that. All right, so we're going to talk about functions, but this time we're not looking at functions the same way as you see functions in your other classes. So this goes here back to the concept of a tuple. So what is a tuple? Can someone remind me, if I want to find the equivalent concept in C++ programming, what is a tuple? Not necessarily a two tuple, just a tuple. Array or vector, okay? So yeah, go ahead.
Container and its order has duplicate values.
Yep, it's a container where the ordering of the items inside is significant. Okay, so that's a tuple. So it's an ordered container where its components are ordered and the ordering is significant. Okay, that's kind of redundant, but I think it gets the message across. Furthermore, a tuple can contain multiple items of duplicate values. So the tuple 112 is considered distinct from the tuple 121 because they both have the same item having a 1, but the second item are different. Okay, one has a value of 1, and then the other one has a value of 2, and at that point, you really tell that these two are different. In other words, if you want to compare two tuples to see if they are the same, string compare is kind of the same deal. Okay, you have to say for each character of each position, are they the same? If for at least one position that is not true, then the two strings are different. And in this case, you can say the two tuples are different. All right, so a tuple is represented by a comma separated list of items enclosed in parentheses. For example, ABC is what I would call a 3 tuple, and because it has 3 items. And I would also use the bracket notation here so that I can designate a particular item in a tuple. And this I, which is serving as the index into the tuple, so I can identify one thing out of the entire tuple, is also 0 oriented, which means the first item has an index of 0. So that is conventional in most programming languages, except for a few programming languages that decide to use 1 as the first. But all the programming languages that you have learned up to this point should use 0 as the index for the first item. All right, so we'll also use the cardinality notation of the set theory to specify the size of a tuple. If T is a tuple, then bar T bar is specifying the number of items in the tuple. So, in the analogy of string, this is string length, but only sort of. Why do you think I only say sort of? Because string length only counts up to, but excluding the null terminator. But the bar notation would include everything in the tuple, so it has no inherent terminator that we do not count as a part of it. So that's why they are close, but not exactly the same thing. All right, so now we can get into functions. So we learn functions in other math context because all of you have taken Math 372, Math 375, or Math 370. You all know what a function is, okay? Because in trig, you get what? Sine, cosine, tangent, those are functions. In regular math, you have log e to the power of something. Those are also functions. So in this class, we also talk about functions, but the way we look at functions is a little bit different. So the way we look at a function is, okay, we'll start with this. Okay, we'll start with this notation here. So f is a function in this case. So if you see this notation, is a confirmation. It's telling you that f is a function. It maps elements from x, which is a set, to y, which is also a set. So x is called a domain, and y is called a codomain in this class. If you have taken math classes, the term codomain is the same thing as range. Okay, which is the destination of the mapping. Are we good so far with that notation? And I did not invent this notation. You would see this notation in other contexts as well as you read more material. So now the question is, so how do we exactly express f of x is 2x as a set? Okay, so the main difference of how we look at functions is in a math class, a function is more of a shorthand, it's actually calculated this way, but since we don't want to repeat all of that stuff, we shorthand it into f of x, and then we assume that we know how it is defined. But in this class, it's a little bit different. So if fx is defined to be 2x, and this is specifying the range and also the domain and the codomain of f. So in this notation, this funny looking z is what? The set of all integers. Very good. So you just know that f is a function mapping the set of all integers to the set of all integers. That's all we know. Exactly how the mapping is done, we do not know. We just know what is the domain and what is the codomain. Are we good so far? All right. So now, how do we know the content of the set? Well, you can try something like this. Okay, you can give people a few examples. Okay, 0 maps to 0, 1 maps to 2, 2 maps to 4, 3 maps to 6. And then, of course, on the negative side, you also have to say -1 maps to -2, blah, 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 and so on. But this notation is always non-precise because we really have no idea what the ellipses mean. Okay, the dot, dot, dot. I'm not sure exactly what they mean. Okay, I can guess maybe they mean, oh, 4, 8 is in the set, 5, 10 is in the set, and so on. But that may not be true. So the way we do it is to use this notation here. So this is where things go a little bit interesting because it's combining something that we learned before, and now we're using it to express f as a set. Are we good so far? So f is a set because we see the braces. So now we are using this notation to go like, okay, so how do we qualify the membership? Okay, how do we know what things are in this particular set? This part here, which is on the left-hand side of the vertical bar, is telling us, okay, every element of this set is going to look like this. It's going to be a 2-tuple where the first value is, well, I should say the second value is twice of the first tuple. Okay, so in that case, is 0.5, 1 as a 2-tuple a part of this set? No, because we have a constraint here that x has to be an element of the set of all integers. So that constraint still needs to be applied so that we can rule out complex numbers as x, we can rule out non-integer numbers as x, and so on. All right. So you can also say the same thing like this for all element x in z, for all y element in z. In other words, up to this point here, x can be 5 and y can be 2, for all we know. Okay, but it's okay because now I can say y equals to 2x if and only if xy as a 2-tuple is in F. So that still gives us the necessary definition of what is in F as a set, and we are still doing it correctly. Are we still doing okay, or do we have any questions at this point of this class? Okay, we're still good. Okay, So the next one is what makes a function a function? Yeah, I know how that sounds, but there are certain requirements. Certain sets, that have two tuples are not functions. So the first thing we need in order for a function to be a function, in order for a set of two tuples to be a function, there are a few things. The first one is really simple. That set has to be a subset of the Cartesian product between the domain and the codomain. That's the first requirement. If f does not meet this requirement, forget it. It's not a function. Is that okay? So do you guys want some examples of what is and what is potentially not? Okay, we can certainly do that. Oh, wrong thing to do, because I was looking for Joplin and I'm not using Joplin today because I can't get the split screen to work today. All right, so what we'll do is, I'm just thinking whether I should use the math notation or not. Okay, I think I'm going to use the math notation. All right, so we'll use a few symbols here. So the first one is F0 because I'm planning to reuse these definitions. So I'm going to say F0. And I want to know whether it is a function that's mapping from 0, 1 as my domain, map to ABC as my codomain. And I will give you what F0 has, membership of F0. So F0, is defined to be exactly 0A, 1. There we go. All right. So now the question is I need that shortcut key. Every time I want to enter the equation, I have to do that. Is F0 a function? Okay. All right, so the first thing we do here is to identify, I want the domain to be 0, 1 as a set. I want the codomain to be ABC as a set. That's what I'm intending to express here. The second part is showing you the actual membership within the set F. So now the question is F0 a function, given that I want 0, 1 to be the domain and ABC as the codomain? The answer is no. We can disqualify as a function automatically right now because because 1 by itself is not a part of the Cartesian product between 0, 1 and ABC. So let me type the answer here. So we can say no, because and go back to insert equation. Because 1 is an element of 0, 1 Cartesian product with ABC is false. Meaning that this is getting old, meaning that F0 is a subset of the Cartesian product between the domain and the codomain. A, B, C. Is false. There we go. Do we have any questions about this answer here? Do we have any questions about why F0, as it is defined here, cannot possibly be a function? It disqualifies it. The first rule disqualifies it because F0 is not a subset of the Cartesian product between the domain and the codomain. Yep.
So is it because like 0 and 1, it's like a two tuple, it always has to basically be like grouped together when doing the Cartesian product?
Well, 0 Okay, so what the first item of the two tuple has to come from the set of 0 or 1. In other words, all the members within F0 should start with an element from 0, 1, and the second one should be coming from A, B, or C. In other words, we have 6 things that we can choose from to put into F0 to at least meet this one requirement. 0A, 0B, 0C, 1A, 1B, 1C. Those are all legitimate things that can be in F0. One by itself, not being in a tuple of any kind, cannot possibly be an element of F0. Or it, one being in the set F0 automatically disqualifies F0 as a function. Are we still doing okay so far? Because I am referencing many concepts that we have talked about so far. Membership, okay, this concept of a two tuple, Cartesian product, subset of. All of those are operators or symbols that we have already defined. Is that okay? Yep.
So if you were to switch A and 1 with each other, it would still be false.
If I were to switch,
So if it was 0, 1 in parentheses and then comma A, that would still be false.
that would still be false. Yes. All right.
Because it has to be a tuple, right?
Yeah, it has to be a tuple, and on top of that, the first thing has to come from 0, 1. The second thing has to come from A, B, C. So even if that is not true, it will still be automatically disqualified.
Seems a bit of a redundant question, but so adding either A, B, or C after 1 would make it true then? Or,
You mean turning into a two tuple?
yeah, so where the 1 is, if you were to add A, B, or C after, would that make it true?
That would not make it disqualified automatically. Because we are looking at, okay, I'll give you a second example. Okay, so this is good because I can give you a second example. So f of 1, same intended domain and the same intended codomain, except the membership in this case is 1B. Okay, so now I should ask the question in a slightly different way. Now I can say, can F0 or F1 be a function? And bad grammar here, because if I change this to a can, I need a B here. Can this be a function? The answer is yes. Can be. All right. So now I can also give you another example, which is a can be, based on the rules that we have talked about so far. So we will define f of 2, and this time, f of 2 is going to contain one more thing. Okay, so we'll say 0C. Okay, and then we ask, can this be a function? And the answer is yes, it can be, but only based on the qualification of the function up to this point. In other words, the only thing we do right now is to ask, let me go back to my slide, because up to this point, the only thing that we care about is whether this is true or not. In other words, right now, if F is a subset of the domain, Cartesian product with the codomain, it has a chance of being a function. If this subset of is false, then it has no chance of being a function. So that means there are additional conditions in order for this F here to be a function. This is only one of them. So this is what we call a necessary condition as opposed to a sufficient condition. All right?
We can definitely say no, we can definitely say yes.
We can definitely say no, but we cannot say yes for sure. Is that okay? So if F is not a subset of the intended domain, Cartesian product with a codomain, then F has no chance of being a function. But if it is, then we have some additional requirements that also need to be met in order for f to be a function, but it has passed the first test, so to speak. Is that okay? All right. So you might want to say, so what else do we need? So the second one is a little bit interesting because I think it illustrates one of my earlier points. In addition to this observation, there's another important criterion for a subset of x and y, the Cartesian product between x and y to be a function. In English terms, okay, it is each element of the domain must be mapped to one and only one element in the codomain. What does that mean?
Function has to be 1-to-1. So each value in set of domain can only map to one value in range. But a range can be mapped to two values in domain.
All right. Okay. So it's ambiguous. It's ambiguous because when I say map to one and only one element in the codomain, does it need to be unique? It doesn't say, right?
No.
It doesn't say it has to be unique. And okay, so let me give you these scenarios. Okay, so let me go back to the document. I'll give you these scenarios, and you tell me whether that is the case or not. So let me give you F3 and then I'm just trying to find out what is the best way to do it. So this is F1, we have F2, and I'm going to define F3. So here's F3. So go all the way back. F3 is defined very similarly, except it's smaller. Okay, it only has 0A in it, not the other two. And the question is, can F3 be a function? And the answer is yes, it can be, but only based on the qualification of a function up to this point. And up to this point means is F3 a subset of the Cartesian product? So can everybody see that F3 is a Cartesian product? It's a subset of the Cartesian product of 0, 1, and ABC. Yes? Okay. So it has a chance because we have only talked about one single condition right now. So now the next question is, what about the if one and only one element in the codomain? Every element in the domain must map to one and only one element in the codomain. And I'm going to go back and change my F1 a little bit because I want to make that specific point and change that to A. Okay. So which one of these is meeting the requirement of every element in the domain is mapped to one and only one element in the codomain out of F1, F2, and F3? Yes, go ahead. Only F1. Okay. So only F1 is doing that. Okay. So I will also write here. Okay. It is meeting the requirement. Oops. Oh. Requirement of being a subset of the Cartesian product and also meeting requirement of each element in the domain maps to one and only one element in the codomain. Okay. So now we'll go ahead and check out why the other two are not working. What about this one here? Okay, what about F2? Why is F2 not working? Because 0 appeared twice. So it is mapping, it's not mapping to one and only one, it's mapping to two things in the codomain. So it's missing that requirement. Okay, so we'll go ahead and point that out. Okay, we'll say at least one element in the domain maps to, does not map, okay, in the domain does not map to one and only one. So, there we go. What about F3? Does F3 meet that requirement? that every element in the domain maps to one and only one element in the codomain. And if it's not meeting that requirement, how is it failing to meet that requirement?
One doesn't count that.
Exactly. So we can say at least one element in the domain does not, same thing, does not map to one and only one element in the codomain. So the question now is, do you think the use of if and only one is important? Can I just say one? Why, what, how are they different?
Well, F2 would then pass. You just said one.
If I just said one, it usually implies at least one. It does not exclude more than one. But if I say one and only one, it excludes 2, 3, 4, and so on. It automatically excludes 0 because just one already excludes 0. But I need it to be exactly one. Is that okay? But you can also kind of guess, oh, but this is kind of not very precise. And as a whole is very wordy, okay, to describe, what a function really is, the extra requirement. The first one is easy, okay, subset of, we got it. The second one, which is every element in the domain needs to map to one and only one element in the codomain, not so easy to express. So in the notes, I do hope that you guys read it because otherwise I'll be wasting my time typing this stuff here. So I went through all the reasoning, blah, 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 blah. And this is the last one, okay? This is the way we can express in addition to the subset thing, okay? This does not handle that. But this does address the part about, every element in the domain has to map to one and only one element in the codomain. So let me try to read this to you. So it says, for every element in X, okay? And remember, X is representing our domain. So it is saying for every element in the domain, the following, which is everything inside the parentheses, has to be true. What has to be true? So we look at, something has to equal to one. What has to equal to one? We see the bar notation. That means we're looking at the cardinality of something has to equal to one. The cardinality of a set. What set are we talking about? So this set here, which is enclosed by the braces, is constructed from every element look like EQ. E is already down here. So we know E has to be an element of the domain. Q is unbound, which means, okay, Q can be anything. What is the requirement? The bar is separating the formatting of an element, which is on the left-hand side, from the extra constraints on the right-hand side. So the extra constraint on the right-hand side simply says EQ has to be an element of F. So that will also, that finally binds what Q can be, okay? So if that can be, that has to be, so this constrains what can be in this particular set. But then the cardinality of the set needs to equal to one. So that really translates to exactly the same thing that we have been talking about, okay? Are we okay with this notation or not? Now, if you want to fully understand what is this notation, you need to read the rest of this. Because this part here, going from here all the way down to here, is the rationale of how I derived this expression to mean exactly the same thing as saying for every element in the domain, it needs to map to one and only one element in the codomain. And it explains the thought process, step by step. So I'm not really just teaching the knowledge part of discrete math, which you can learn from Wikipedia, but I'm also trying to teach the thought process of how things are derived. Are we okay so far with this? Yes.
So, back on the video,
Yes, I can bring up F3. So there we go. And this is F3. So F3 says 0 maps to A, but it doesn't say anything about 1. So 1 is also an element in the domain, but the set does not say Or you can say, it has, one is mapped to 0 of the elements in the codomain, and therefore not meeting the requirement of one and only one. Right. So this for all, okay, let me switch back to the note here. So having one element in the domain not meeting that requirement is enough to fail the universally quantified expression, because in the universally quantified expression here, we need this thing here, everything inside the parentheses, to be true for every element in X. So that's why the quantifier is important, because it says you don't just look for one thing and say, hey, this one meets the requirements, so everything is going to be cool. No, I need every single thing in X to be mapped to one and only one thing in the codomain. Can they map to the same thing? Sure. No one says that two different things from X cannot be mapped to the same thing. There's no such requirement. It just has to map to one thing in the codomain. Can we leave things in the codomain unmapped? Yeah, there's no extra requirement saying anything like that. So your job before Wednesday is to finish reading the entire thing and also to read the next reading module. So I have to be careful with what I'm saying. So you should finish reading functions as sets, but also to finish reading injection, surjection, and bijection, because that is when things kind of come together. Okay, there's a reason why we need to talk about bijection. The assignment is due on Wednesday, right before class. So, okay. So let me see if I can find that link. So right here, it is due on February 1st at 12 p.m. Yeah. The best way is to open it. Once you open it, it doesn't have it doesn't give you a timer, like you have to answer within 2 hours. You can wait all the way until like 11:59. You probably won't need 2 days, but you might need to study a little bit, kind of think about things a little bit, look up on Google a little bit, or even chat GPT a little bit. But use that time, because the more time you have, the more time you have to absorb the concept. Yeah.
There's no roll today?
I did not take roll today. That is correct. You didn't catch any more mistakes today. So.
Yeah,
I have a good day. That was good. I like it. And by the way, the mistake that you found, I think we can simplify the definition. So one of the introduction is not even needed. So E intersecting with A intersecting with E, it just needs to be A.
Oh,
I
yeah.
don't even need the.
Oh, so you don't need the extra conjunction. Okay, that makes sense now.
Yeah.
Sweet, thank you. You have a good one.
You too. Right.